and types of complexity and all kinds of stuff around complexity. Uh, this paper, the whole of this paper is is the subject of matter of complexity, and what is essential complexity, and what is accidental complexity, and what we do to, and why it doesn't matter, and what to do with those. And that will be the subject of the conversation today. Okay? Do feel free to stop me at any time. This is supposed to be a conversation, right? Okay, you have not drank enough to start discussion. Okay, I respect that, but this is supposed to be a conversation. This is an enormous paper. It is impossible for me in 2 hours to cover everything the paper talks about. It's one of the biggest papers I have ever read. It's 66 pages long, which for a research paper is about the size of a book, right? I mean, a small booklet, but still, most papers I have read are 8 pages long or something like this. This is just big. So we will not cover everything in the paper. And to be fair, there are several problems I see in the paper that I will not cover at all. But you can see Sarah May has tweeted a lot about that, if you want to see the problems the paper has. In some aspects, just to talk a little bit about this, the vision the paper writers had about object orientation is really flawed. But let's forget about all that. Okay? This paper is about complexity, and the subject is very interesting. And this paper I will disrespect this paper a lot today. I love this paper. I will disrespect it a lot today with you. Because the entire goal of this paper is a very noble goal of changing the language we use themselves, making them evolve, right? And what I want you today is to grab some quick wins from this. I will just steal some ideas from the paper and say you can apply them today in your code bases, right? Which is by nature something that probably the people that wrote the paper will hate me for. That's part of this deal today, okay? Because they really wanted to change more profound things, the language themselves work. I'm more of a prosaic goal here. So, hi, can you hear this? Do you want it bigger? Who wants it bigger? Okay. Who still wants it bigger? Who still wants it bigger? Good for everyone? Okay. Hi. I'm Romeu. You can find me on Twitter. And I do organize a little conference in Paris that some of you were. I must know for this, which is the reason why I'm doing this talk today. This is the reason behind 5 or 6 of my talks. Is this tweet. So I'm trying to correct this problem. This is the problem I'm trying to correct during the last years of my life. And we're talking about this paper. So let's start. This paper had out of the top it has a bad reputation because you can have 2 completely different readings of this paper. Completely, absolutely different readings. Depending on what are your own definitions of some basic words. And the paper never bothers to define them. So let's start by that. Let's start by that together, okay? So my first question for you people is, what is simple? What is simplicity? That's not a very easy question, but we really have to discuss this one in the beginning, before even starting the paper itself. Because the author had a very specific definition of the word simple, and if you don't have that same definition, the whole paper changes completely. So what is simple? Anyone want to try? Oh yeah, yeah. Thank you very much. I'll note some of those. not complex. Easy to understand. Someone has another definition? There will be a lot of typos today, right? Let's just forget about those. Few moving parts. I love that one. Well, the definition of the author is more on the lines of this one than the others. Actually, it's a very weird little thing, is that there are several words in the English language. I don't know if in your language it's the same thing, but several words in the English language that just change in meaning over time. It's a whole evolution. And some of those keep changing back and forth. For example, the word nice. The word nice started as being kind of an insult, and afterwards became kind of a positive word, and then negative again, and then positive again, then negative again, and now positive, since a century or so. Okay, and through history, the meaning kept changing back and forth over the slices of some centuries. Okay, and the word simple is a word today that is very subjective. Everybody, it's like love. You know it when you see it. You know it is simple inside you, but you can't really agree with another person on what exactly is the meaning of it, right? Everyone have a very subjective approach of what is simple. So if I ask each one of you, I will have several different definitions with some intersection between them. And this was not always the case. Some centuries ago, the word simple was a very objective and boring word with a very definitive meaning. Okay? And we all, mankind, have stopped to use the word in that sense. And the paper uses the word in that sense. Right? So, gotcha. As long as you know that, everything makes sense, right? So, let's start by correcting that problem, okay? The word simple, I swear to you, this will be the most boring part of the whole talk. But I kind of need that one. The word simple, eons ago, meant not compound. Now, what is compound? Who knows what compound is? Well, not compound is very specific, right? It's just the reverse of compound. What is compound? That's a way of seeing it. Have you seen the term compound interest? Yeah. Compound in finance, compound interest is when the output of your interest becomes one input of your interest. Okay? So you lend some money, and now the value of this is getting bigger, and the things you owe more because of that interest becomes a source of the interest itself. So when you have a flat interest, you just take as input the money you lent, and you put the interest, and you have a final value, right? When you have a compound interest, each month, the little bit of interest that you came back goes inside the equation again. We are in the specific meanings of my output becomes one of my inputs, right? And it's a fixed thing. When you lent your house, you probably had a compound interest. You can know beforehand how much it will be, because if you have the input as an output, it's something that becomes smaller and smaller and smaller and smaller, right? It's just a big impact there. I can see I'm boring you guys with this, girls and guys with this. So just keep the very slice of life of, I have an output that becomes an input, and that output that becomes an input hangs the whole thing, okay? Okay. What I defend is that complexity eats compound. When you have a little bit of complexity and another little bit of complexity, the two together are bigger than the sum of the parts. because the output of each one becomes an input on the whole system. Okay? That's the hardest part. If you got that, then everything else from now on will be easier. Okay? The paper never bothers to explain that. It just assumes you know it. Okay? I mean, it's obvious, right? It's very simple. So, complexity in the meaning of the paper is attached to the meaning of compoundness. Okay? As soon as we have that, I'm not doing the paper in order. This is not the point of this. Okay? As soon as you have that, we start with a bigger problem. Okay? If you want to reduce complexity, if every bit of complexity that you have is something that you want to reduce, okay? Do you want to keep some? Is there some complexity over there that you out of masochism or another more important reason, you want to keep? Someone? Yes? Yes? What is it? There's a thing. There's one possible thing. The thing is, the paper starts talking about essential versus accidental complexity. Just a quick tour. What is, for you, not the paper, not the universe, just you, be egoist in this, you personally. If I just ask what is essential and what is accidental, essential complexity and accidental complexity, what is your own definition right now? I know you did not have one up until this point. Just try to have one inside you. What is your definition of accidental and essential complexity? What is essential? What is accidental?
For me, the essential complexity is the complexity of problem space, and accidental complexity is complexity of solution space.
That's one definition. Do you have others? That's a good definition, but that's one. Do you have others?
Essential complexity is probably mathematics. You need some fundamentals.
And accidental, everything else. There is one of, I keep forgetting his name because it's a Japanese name and I'm awful with names. But one of the guys that created the lean, created the Toyota way, he has a definition of waste that is very pertinent to our current situation. Okay? He said, when you screw a screw with a screwdriver, okay, each turn of the screwdriver up until the last one is waste. The last one delivers value. Okay? Which means you still need to do the other ones. But if you start before, there is no value in this. And each one you did before it was necessary, but was necessary waste. Okay? Which means if you can somehow, you could do half of the turns and still screw your screw, you will still want to keep the last one. But you will probably, if you could magically just do half of them, you could probably try to optimize the others. Right? If you find a way to optimize the others, you will. But even if you find a way, the last one, you want to keep it. Okay? No?
Why do you need the last one? Let's optimize the last one as well.
Because the last one is the one that delivers value. If you don't, the last one is the decision that it was screwed enough. If you don't do that one, it is still not screwed enough.
Yes. But our goal is to reach that state when it is screwed enough.
Yeah.
It is not necessarily to do the last screw. If you are talking about optimization.
That's just a metaphor, right? The whole idea is what you want is to be screwed enough, and is not the whole path towards it that is important. In different ways, we are probably saying the same thing here. And
Actually, I don't think you were saying the same thing, because you're trying to exemplify a binary option with a gradient.
sorry, I could not understand you.
You are trying to exemplify a binary option, essential or complexity, with a gradient. Because screwing in a screw, there's not a single point where the screw is screwed in enough. You can always screw it half a screw more or half a screw less, and it will still.
But there is a point where if you stop there, it delivers the value.
Not necessarily. If you stop there, you deliver some of the value until it gets loose. If you tighten it more,
Yeah, of course. There is maintenance afterwards, etc., etc. Of course.
it's a gradient.
Over time is a gradient, yeah. But at some point you stop screwing, right? I hope so. And you have some form of measuring it. So this is the separation of accidental complexity and essential complexity. In the paper, we have several different ways of doing it. So we talked about it in the pure theory, talked about it in algorithms, talked about it in real life. What I want you, I will describe how it does in the paper. We will describe together how it does in the paper for all those three separations. It does three different separations of what is extension, what is accidental complexity. What I want with you is that no matter what are those of the paper, have yours. Through all this talk, have your separation. That's the important one, okay? Because even the one from the paper itself is a little bit higher than your real life situation, okay? And what is important is to have yours. In pure theory, you have a magic genie. I give you a magic genie, okay? That everything works by magic. So there is no accidental complexity in pure theory. That's an empty, because there is magic, it is empty. You need none, okay? Do you still have some essential complexity?
Depends on the genie.
You don't know which genie you have, right? but that's a very good starting point. Do you still have any essential complexity in that scenario?
You still have to specify your wishes.
You still have to specify your wishes to the genie. That's the essential complexity. You still have to describe the problem, right? So in pure theory, essential is describing the problem. And that can be very hard. That can be very complex. Yeah.
But do you actually need to describe the problem? Can't you just, say
Do what I mean. That he answered that in the very beginning. It depends on the genie. You still have a inherent problem, is that declaring what you want is very subjective, and you can end up with a result that doesn't please you.
There's
If it
many anecdotes about not precisely specifying your wishes. Most of them are actually the same.
That's the point. You have several histories about this, right? We can tap a lot of this. And if you have a genie that is in very good faith, he really wants to help you, all right? Even if you're there, you still need to be very careful about misunderstandings, right? And so in that situation there, describing the problem is still essential complexity, okay? Okay. In the pure algorithm world, in paper, when you're doing paper, you have perfect machines. Network has no latency and has an infinite throughput. your memory is infinite. You never have errors. It's this perfect world, right? It's perfect idyllic world. Okay? In this world there, I still have the same essential complexity that I had before. But is that all? Or do I gain further essential complexities? Yeah, you don't have a genie anymore, so you kind of need to implement these rules, right? But and you have now, it's just in the algorithmic world, but you now have some accidental yet mandatory complexity. Complexity that is accidental, but you cannot live without. What will be it? You start having it because you don't have a genie anymore. It's not magic anymore. What would you have?
Maybe you are bound by the physical laws, like time, for instance. Maybe you assume that time doesn't exist in
Time is an external system. It's just a parameter. It's a very beautiful world of paper, right? Paper accepts a lot of things.
Or maybe testing.
I could not hear you.
Testing.
You need to test, maybe. You need a language, right? The language itself is accidental complexity. You need a way to describe things, to write them down, okay? And you start having, maybe, if you do some little design, maybe start having what we call later control. We will get back to this word, okay? It will make sense later. Okay. You don't have, in this world, you don't need any accidental but not mandatory complexity, right? You just have accidental complexity that is mandatory or essential complexity. Now let's go to the real world. What do we add that we did not have before? Machine failures. That's one of them, right? Sorry? I can't hear you really. Oh, we aren't here. Okay, sorry. I'm really sorry. Accidental, mandatory. We will have error handling. We will have and we will have accidental but avoidable complexity. What we will have? There's a lot of it. You have a lot of it. Don't.
Bugs.
Yeah, misunderstandings. Let's say misunderstandings.
I think we are back to theoretical world.
Sorry?
I think we are back to theoretical world.
Yeah, of course.
Architecture, constraints.
Let's put this in mandatory.
If you are forced to use a tool that's not
Frameworks.
frameworks.
Frameworks. I'm not saying you should stop using all frameworks, okay? And that's not my message. It's just that it's optional, right? It's something that you added, add some complexity. Okay. That's architectural constraints. But I can add here micro services. Okay. Okay. We started having a kind of a list here. We'll go back to this list. What causes complexity? In this first part, we are just trying to understand what is complexity, okay? And then we're trying to find the root causes of it. And once we have this, the paper will attack ways to fight in it. But to fight, you have to identify it, right? So, kill the real world, right? I mean, well, life would be way easier if you did not have any users. So, what causes complexity? What are the sources? The paper has several, but there are two here that there are several. We start with two that are very big. Control, we got back to this later. Let's start with state. What is a state? What is a state for you? That's not an easy question because that's something that you have every day, but it hurts, so you don't want to talk about it. God damn it, you have read the paper. So, usually when I ask this question, what people tell me is my memory. And that's not completely false. But the paper uses a very specific definition of state, which is very important for the rest of the discussion, which is all the possible states you could be. So states use states. Okay. Let's put it another way. When you have a Boolean, a single Boolean in your application, you have two possible states: true and false. Okay, that's an easy one. If I have two Booleans, how many states I have? 4. If I have 10, 1,000 to 4. If I have a single integer and a Boolean, how many states do I have? Yeah, right? That's the thing. My number of states is the cardinal product of all the possible states of every one of my members, right? So for a single object, if I have a single object, the number of states is all the possible states of all its members, all its attributes, right? No, there's no Schrödinger object. You can always calculate, but it's very big. Which brings me to, if you have a single string, how many states can you have? I'll give you a hint. Yes, of course. But in the language you're using today, if you have a single string, you take a string as a parameter to a method, right? How many possible states can a method take?
Well, there is no name for this number.
Thing is very big. It's very, very. I give you a hint. All the works of Shakespeare in Korean and Japanese is one state. Right? It's just one possible input. And when you create a method that takes a string, what you are saying to the word is, hey, you can pass that too to me. This is one possible thing it accepts. All the works of Shakespeare in Japanese and Korean. And another state can be the works of Shakespeare in Japanese and Korean with typos. Right? That's another possible state. Okay? And, yeah.
I would say that counting the states like that isn't really relevant because the states collapse.
Do they?
You literally only have a few states that you actually care about.
Yeah. That's the whole point of this conversation. We're getting there. Don't worry. What you're saying, when you're putting that contract up, what you say is, I accept all those states. And who here has strings as parameters? Okay. Keep your hand up if you accept as one possible input all the works of Shakespeare in Japanese and Korean. If that's okay. Okay. That's always an option for you guys. I'll believe you. Most people don't. Most people collapse. Most people are in the situation that he just described. You just accept a subset of your possible states. Okay, so the problem is, if you accept that you can create an object in one of its possible states, I mean, in any object you create, if you take all those members in constructor, and if your object is immutable, you could, theoretically, any of your objects you can create in any possible of its states, right? Not a problem. Not a problem. Okay. So if you can do this for one single object, you can probably do this for all your objects. Yeah? If you can do this to all your objects, you can probably do to your whole application. You could probably start your application in any of the possible states the application can have, right? So for a single object, the number of states is the whole product of all states of these members. And for an application, the number of states is the whole product of all the possible states for all the objects of the application. And for a whole IT service is the whole possible states of each application multiplied together. Okay. If you are taking that logic further, if you are pushing the logic further, this means that I can probably I could probably be able to start any application in any single of the states the application could have. And I could probably start my whole IT department in any state of the whole IT department could have. Do you do this today? Who here is able just to start the application in any possible state the application could have? Nobody does that. And yet, why not? Okay. So, what I try to come here is, if you did this, most of your states would be useless, would they? Most of those states will have no meaning. Like he said, it coalesces. I'm communicating a capacity of having a whole lot of states that most of them don't have any sense for my application. Well, this is a formal complexity. And that's where we enter the realm of reasoning. This is a central point of the paper. I call it understanding versus reasoning, but the paper calls it formal reasoning versus informal reasoning. Okay? Tomatoes, tomatoes. Thing is, it's very easy to read code. I mean, should. It's harder to understand everything that possible piece of code could do. Right? To grasp the entirety of the behavior of the code is a harder task than to read code. Does anybody has a problem with this phrase? So, reasoning is coming to the term where you understand all the possible behaviors of your code. You could do that in a very formal way. You could do formal proofs and something like this. I'm not inviting you to do that, but you could. That's an option. Okay? Other ways of reasoning your code is just reading it, or creating a lot of tests that show all the behavior, or etc., 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 etc. And the whole idea here is that your number of possible states creates a difficulty in itself in reasoning the code. Does anybody have a problem with that? Even if most of them coalesce, an application that has lots of states is harder to reason than an application that has fewer states. Okay? And to that level, one of the sources of complexity is the numbers of states you have. Okay? And even if it's a little bit provocative when I say this, it's not completely honest. If you take out a single Boolean out of your application, you just halved the number of states the application could have. And if you add a single Boolean to your application, you just doubled it. Not only the application, but because everything is just multiplication, if you take a single Boolean out, you just halved the number of states of your whole IT department. And when you add but a single Boolean, you just doubled it. Okay? And hence, that's what I wanted to get here. Hence, we go back to the definition of complexity. When you doubled it, you add to the compoundedness of it all. And you rendered the reasoning harder for everything, little by little. So the whole thesis here of this paper is removing just a little bit of complexity pays, and keeping doing it, the work of just removing those little bits pays. So one quick win here is all the states I have possible states I have that are not meaningful are accidentable but avoidable complexity. And you have a lot of it. It's not essential complexity. Those states that are useless are not essential complexity. They're not essential but mandatory complexity. They are just accidental but mandatory complexity. They are just accidental but spurious complexity. It's just there. They diminish your capability to reason about the code and add nothing. So why do you do them?
Because it's hard to identify this sort of state.
Well, I mean, aside from the people that say that it would accept all the works of Shakespeare in Japanese and Korean, and please talk to me afterwards to explain why. But except for those, as soon as you add a string to a method, you kind of know you're doing it, right? Deep inside, you know you do not want every possible value, but you still do it. Why? We all do it. I do it too. Why we do it? Because it's easy. And that's the thing. Simple is not easy.
Probably the set of strings isn't well defined. So you do probably have no source of information for the exact set of strings going to accept. So what do you do? You check.
That's another reason, a very valid, important reason. You're dealing with the unknown. You cannot define formally what you want. But maybe you have better than just everything.
You can always
So the paper also talks about mutable versus immutable state. Thing is, a state where you can change is in itself a more complex state than a state that I cannot change. The act of being able to change it adds to the complexity of it. And maybe it's mandatory, maybe you need it. And that's fine. Okay? But just adding because it's your default option is also an accidental complexity that is not mandatory. So it's just there. It's just creating a more, just little by little adding to the complexity of the overall system for no benefit. the paper invites you to challenge is your notion of default. There are several things that you do because they are the default option. And those default options are bad. Are bad because they cover lots of grounds of what is needed, but it's not needed by everyone every time. So reducing what you promise and what you deliver is reducing the overall complexity in itself, and is saving your ass. So what I usually say to people is, immutable state is the closest thing we have to real life. Real life is immutable. Mutability is just a thing we created in your mind. In real life, nothing ever changes. There is a Greek philosopher that said that way before me. I had not invented that idea. I keep forgetting his name because I keep getting Heracles in my head, but that's Hercules, right? That's not the guy. And he said you cannot cross the same river twice. That's not possible. It's the same thing for state. As soon as you take into account time, then you understand that in real life, you cannot go back in the past. When you cross the river once, the river you crossed back is not the same river again. When I moved when I moved my phone from here to here, I create a motion of, okay, let's not go to motion is impossible today. I created a motion, but the position of my phone in t-1 is still here, and I cannot change the fact that it was here before. Okay? So as soon as you accept that real life is immutable, is an append-only thing. A state in real life is append-only. The fact that we accepted to change things in memory was just because we're lazy. We did not want to make things closer to real life when we did it. Okay? Yeah, right? So the paper goes a whole deal about, there's several larger places of the paper that I'm not going to delve into because we will never have the time to. But the paper goes a whole deal about the complexity of mutable states. And I try to just go over really quickly because I think most of you probably agree with that. I mean, who disagree? Who says that mutable states is very cool here? No? Right.
Well, I've been thinking about this since you introduced the state, actually, and I actually don't think it's the state itself that causes complexity. Even like with the multiplying level of states you get, that's not the complexity. The complexity is in the transitions between the states. So if you have a billion states that all has a single transition to one other state, then that's one transition. And that transition is the complexity of the application.
But if you have billions of states that has a single transition, you still have to reason. What you have is several billion transitions to the same place. And you still have to reason those. So,
No, because it's just one conceptual transition.
if you know it, do you always know it?
Maybe.
I mean, who here has read all the code bases, every line of it? Yeah, right. Who here knows every possible transition of their state? You all know that some of them are not there, but you know all those that are not there? That's the whole point, is the compoundness of it. For a single variable, is never really a problem. It's the fact that you have it in all the code base that is a problem. You feel it? I can have in a single, sorry?
I think it's also one of the things that we do in the algebra design is making implicit explicit, right? So that the changing of the state, like infinite state, one string to another string, is very implicit.
Yeah.
And what we need to do to decrease the complexity is to make it explicit. So like, you can't change a string to a string. You need to have more explicit.
I mean, I'm not very dogmatic, right? I'm not. So I can accept that you really have something that goes string to string. It's what you do with it is important, right? Maybe it's the identity function. Well, all right. Maybe just truncate things, just strings. Okay. I'm not saying you should not have any strings ever in your code base, but what I try to tell you is you are overusing it. That's all, right? You are overusing it. We are all overusing it. Okay. Well, we could, the paper doesn't, but we could interpret this by saying one possible solution is value types, right? It's just one way to attack the thing. The paper never talks about value types. I just go and try to glue to some small DDD, because we are in the DDD meetup, some small DDD parts. Okay, just to exclude the whole most important part, because I know some people will ask this question. Why am I doing this talk in a DDD meetup? Do you remember the blue book? The domain-driven design, and there is a tagline. Do you remember the tagline? Yeah, right. That's the reason. Sorry? Tackling the complexity at the heart of software. Okay? Is that a thematic reason? We are in the same team, even if there is nothing inherent to DDD when we're talking here. Their goals are the same. Okay? So, state is a source of complexity. It's not the only one. And if it was the only one, it would be way too easy. We would not be having the discussion. Control is the other big one. There are several ones. We give a little list. But the two bigger ones, we which stay a little bit of more time, are control and state. Control is all the code that is there just to handle other code. That's a harder one. That's why I left after state. You have a lot of code that is needed. Some of it is really needed. I'm not dissing it. That is there just to handle other code. Okay? Your code cannot only be just a huge list of business rules. That's not possible, right? You still need other things. Error handling, or every time you do a little bit of design, you're basically creating control. Each design pattern you use is there not to change the behavior of the code itself, but to manage the complexity of the overall software, and hence you're creating code that is just there to touch other code, but it's not there to deliver the business value itself. Okay? This is not bad in itself, because otherwise it would be impossible to handle the complexity of the whole code base. But each time you take a design decision, you're adding a little bit of complexity in order to try to reduce the overall complexity. It's a trade-off. Okay? It's always a trade-off. All design is but trade-offs all the way down. So it's not bad in itself. I'm not saying control is bad. And I'm not saying state is bad, right? It's just that you have to look at what is needed or not inside it. That's all. And you have all this code that is there just to touch code. This is control. Okay. A huge source of usually when I ask people what are the difficulties with legacy code, what people usually answer me, and maybe it's not your situation. Let's talk about this. What the people usually answer me is just finding myself. There is so many of it. That's just finding where I am and what it all does is in itself a complexity. Do you have this problem? Have you ever had this problem? Yeah, probably most of you, right? Who here has never had this problem at all? Okay, no one. So, so this is the complexity of control itself. you kind of get lost in all of it. We will get back to it when we get to reducing those complexities. So I was just showing sources of complexity. All the thematics of this beginning is just to see what is complexity, to agree with one of definition, the author's definition of complexity, and try to see ways of identifying the real life. And then we talk about solving it, right? So after state, after control, what do we have? Those are the big ones, and we have smaller ones. There is one that is very dear to the authors. Power. Thing is, your language allows a lot. The language we use today, and the paper wanted to solve this issue, wanted to make the language more precise, more constrained. But let's not go there. Let's just assume you will still use the language you use today for a while, okay? And then we will just not change like this, okay? It goes to the issue of power. Power increases complexity because you have very generic ways that serves lots of use cases and try to solve everything. And so they have uses that are more complex and that make sense in few situations. And because you have it, you end up using it. For example, your collection API, you have collection lists, for example. They are mutable by default because some people need it, and you just assume that if you don't need it, you won't use it. But because they are by default, people take those options by default of the language and emulate them, copying them everywhere. There's one way. Languages have an enormous set of choices, and sometimes an enormous set of past errors that people really regret, but it was in the past and they cannot really completely solve them now. That are just there, and impact how you do code. Who here has ever done Java? Do you remember? I mean, it's not really true anymore with Java 8 and with Guava before that, etc., etc. But we remember some ages ago with the collections API of Java, how they did copy of collections. No, anybody is old enough to remember that? Okay. Nobody. It copied them in place. Like I mean, you just passed the arguments and it changed the argument. It was awful. It's just but an example. The decisions of the language itself impact your code. Okay? And you have and you have what other people did before that impacts you too. Bad design interfaces that you have to call is an external thing you have to call in them, and they impact you with bad design decisions that increase your complexity. How do you solve that one, please? Do anybody here has any idea? That's a not very legal one, okay? You isolate them. So I'm not advocating for any specific design pattern ever, and all design patterns are good in some situations and bad in others, and there is no silver bullet, but you really are not using adapters enough. They are very good, you should. And in DDD we talk about anti-corruption layers. The whole idea is what other code, the way the other code is done impacts your code and increases your complexity. And the way to fight this, when you still need to talk with it, is to try to encapsulate it over. Try to create a translation between contexts where your context is all clean and the other is not. This would not be the approach of the paper, but we'll get to it. We'll get to this approach in some seconds. Do you see another source of complexity other than those ones?
What about the behavior? The system behavior, the essential behavior. I think that's the most complex one.
Is a source. And we cannot do very much about this, right? But it is one. Well, there are others, but those are the main ones, but there are others.
You also have this problem with APIs that not used anymore, but you don't really know.
Depreciation.
Like you have to support something that is never used. You don't really know.
And that's where we get to frameworks. I'm not saying the frameworks are bad. This is not a rant on frameworks. But as soon as you use any framework, what you're saying is, well, I'll define frameworks by the code that calls you instead of you calling them. When you call them, this is a library. When it calls you, this is a framework. In that definition, the framework defines your design. I mean, constraints by itself your design. And so it takes the framework itself dictates some design choices in your side. And as soon as you accept that, those decisions can be bad decisions relating to the complexity. And you cannot do much about those, right? But maybe there is a value there. I'm not saying frameworks are bad. Okay, once you have all those, how do you fight them? We have seen together a definition of complexity and ways to identify that complexity. How do you fight that complexity? Decrease. Oh, yeah, we could try that. So we could try to remove to decrease all the number of states. We could try to decrease all the possible control. We could try to decrease it everywhere. In the ideal world, we would. Okay? I think I have nothing else to add you. The paper could have stopped there, and it did not. So we are about 20% of the paper now. So so the whole idea is you have to focus on somewhere. You cannot just pay the whole technical debt of your whole application. That's not really feasible. I mean, that's very expensive. So how do you do? What the paper tries to convince you is that there is an enormous value to design your application separating what you consider to be essential complexity and what you consider to be accidental complexity. Okay? If you know that some accidental complexity is mandatory, just by splitting the application in, I have essential on one side and accidental on another side, then what happens? In the essential side, what I have there is the part of my code where I really would gain benefit from destroying the complexity as much as I can. I could go all the way and try to do freaky things that I don't think are really useful in my whole application. Okay? What I did is I just took the application, I extended it, right, split it in the middle, and start separating things. And in one side, I try to do as small as I can. So it seemed useless because the overall complexity of the application is not reducing. Actually, it is. Like I said in the beginning, well, I said the example in state, but you can apply to everything else. As soon as you remove a single slice of complexity, you are reducing the overall complexity a lot because of the components itself, right? So by separating it, you can concentrate, focus your attention, and reduce it. So when you separate the whole idea of essential and accidental complexity, the essential side of it, like I said before, and that's the tricky part. Like I said before, you can always instantiate your objects in any given state of they could be. That should always be possible, right? Well, then you can probably take all the state from the essential part and put outside of it. That should be possible too. That doesn't make sense right now. Okay. Let's suppose all your objects are, there's just a supposition, okay? That would be seen kind of wild imagination here right now, but let's suppose that all your objects are on the essential side of your application are immutable, okay? You try to fight the complexity of state, and you say, well, I separate it in two. One side is the part I consider essential, and the other side is the part I consider it accidental. Okay? The part I consider essential, I try to make everything immutable. Now that everything is immutable, then my constructor is just a syntactic sugar. This will be a complicated phrase. My constructor will be a syntactic sugar for partial application. Once I did that, so when I did new, I passed arguments, dot method, where I call with other arguments. This is the same thing as have a single function that take all these as arguments, right? And I could apply just some parameters of that function. When I did this, then everything in my essential side could be done just with functions. Okay? I not say that should, but it could. Okay? If everything on the essential side could be done just by functions, then everything is just parameters. I don't need a state in the essential side at all. I just need to pass parameters to it. Yeah? When you did this, then what you end up with, in one side you have your essential complexity in pure functions that only take parameters that have no state. In the other side, you have code that just calls it, controls it, and state. Yeah? That's not a simple issue. The paper actually draws this, so let's try to find what it does. And this is a very bad idea. Yes. See? Can everybody see it? I could have essential logic, separate the essential state from the logic, and have accidental state and control. That's an intermediary step. Once I did this, now I have an area of my application that just has the essential logic and it's just pure functions. And those pure functions could be completely referential and transparent, could be completely stateless, could be I could do a lot of things to reduce the overall complexity of those. I could invest a lot in that side. towards reducing complexity, right? And I will still have this area here where I did almost nothing, but it calls it, right? Well, what the paper defends, and I do believe, so what I'm defending to you today, is that if you split like that, you are already reducing the overall complexity of your application by a lot. It takes time to do this. Holy shit. I don't know what is the problem there, but it's a technical problem with it takes some anyway, it takes some time to achieve this, but if you do it, the overall complexity of your application diminishes. Do anyone here does not see why? That's an important point, so I cannot just gloss over it. Have I lost some people here? Do you see how would you reduce the overall complexity if you reduce the complexity of that part? So we don't do that today. Usually we don't. We don't bother doing this today. We do not separate over that line. There's not a specific line that is very important to us, right? We separate over several things, and design usually separates lots of things. But this is not the line that we're using today to separate stuff. What the paper tries to defend that we should. And so code inside the essential part should never call code outside it. Should not know that exists codes outside it. It's a very extremist approach to coding. Okay? But if you do it, what happens is that the code inside the essential part becomes very, very similar to the whole theoretical world we had in the beginning. Not the genie part, but the algorithmic part. Right? It's very naive code that doesn't bother with the whole problems of real life. It just tries to solve your business domain rules. Okay? That code is it lives in the fantasy world. And that fantasy world part of your code base documents all your business needs. Now, there's something I found quite interesting, is that in the very beginning, when I ask you what is essential complexity, and I talk about the genie, the very first thing every time I did that presentation say is describing the problem, right? What I find interesting is that in most code bases I have ever saw, people usually don't do that. It's the most essential part, but people usually don't do it. Usually your code base describes a solution to a problem that is no longer described. Yet you agree that it's the most essential part. Why? If it's so essential, why nobody does it? Now we could, if the paper talks about that. The paper really talks about that. We could describe more of the problem. And we could not only program by describing the problem, but we could program by doing a lot of problem description. And there are languages that oriented to try just that. Who here has ever done Prolog? Or other languages like Prolog-like languages? So it tries, right? It really tries. It really tries. You are describing the problem more than you are describing the solution. Okay? It's not perfect. You still have to describe some of the solution. But your program is more a description of the problem than is more a description of the solution. And most of you are not doing Prolog right now. Who is doing Prolog in their work right now? Or something similar? Right, nobody. And that's the thing. if it's so important, then in the essential complexity part, you should end up, not exactly using Prolog or something like that, but you should end up describing a lot more of the problem than you are describing the solution. You are describing what you want to achieve more than you describe the solution. It's not specs per se, it's code. But it's code that describes more, that is descriptive. And this is all very Fantasyland. I said in the beginning, what the author wanted is not necessarily applicable to your real life today, but the ideas behind it are. Okay, maybe you will not separate that much. Okay? Maybe you will not separate as much as I hate it. This is awful. Maybe you will not separate as much as the author tries to convince you to do it. Because the author wants to change your language. We will get to this. The author tries to change your language. But today, you can go towards that direction and do something and gain something from it. And that's what I'm trying to make you see it today. Okay? Even if you do not go as far as doing that, and he goes farther, we will go farther with him. There is a way more milder transformation that is in that direction that you could do today. Who here has heard about hexagonal architecture? Okay. Hexagonal architecture, which is also called the ports and adapter architecture, which is also called the clean architecture, which is also called the onion architecture. Okay, there are several names for it, and you can find it easily on the internet. But what I just described here is not exactly hexagonal architecture at all, but hexagonal architecture is a step towards a milder step towards that. What hexagonal architecture say is, well, you separate your code in two, inside and outside, and in the inside you just put the domain logic, and outside you put everything else. And the domain, you call the domain, from the outside you call the inside, okay? So what's the difference between that and what I just said here in Out of the Tar Pit? The difference is, in Out of the Tar Pit we are extremists, okay? This never know, the essential logic part never know the outside exists. In the hexagonal architecture, we do not find it important to separate the state and pull the state out. Everything has state. The inside and outside of the hexagon have states. Okay? And in the hexagonal architecture, the inside can call the outside. If I make a call and it needs, I need a little bit of domain logic, and that domain logic needs to call the database, it can. You just have to communicate with the outside of the hexagon, but it can. Here it can't.
You can certainly hide it in an interface. You use interfaces so to abstract the database.
Yeah, that's what hexagonal architecture does with ports, which are then you plug the database to a port and you talk with it, and you abstract it out. But the whole point in Out of the Tar Pit is that essential logic is not only doesn't know about the database, it shouldn't communicate with it at all. But as soon as it has a dependency at all, even if it doesn't know what is it, is to add into its complexity. So this approach here is much more extremist, right? You get to the point where you just cannot have a call outside. It's just in a single direction, okay? Which is not the goal of hexagonal architecture. In the hexagonal architecture, my domain logic can still talk with an interface that talks with the database, and that's good. And you probably should do that, okay? And Out of the Tar Pit, you don't. So you just have the control in the middle, this thing here. And that thing here asks several questions to the domain logic. So it has a little bit of the domain logic itself, right? It has to. It asks a question to the domain logic, and it has half of the answer, and it has to talk to the database and pass those results to another question that it asks to the domain logic, etc. It loops, it asks several things to the domain logic. And domain logic is very static. It doesn't talk with anything outside it. It just exists. Okay? That's the main difference, and that's a very big difference, and a very extremist way of doing things. Okay? I'm not prescribing anything. I'm not saying you should absolutely do this or that. I'm just showing an approach that the paper shows. That's all. Okay? Well, later in the paper, he will separate those further. I hope to get this quickly. Here. Oh. It has the very beautiful name order. That's an awful name. I hate that name. Oh, damn it. So I hope that it doesn't do that tomorrow, right? So tomorrow I'm giving a talk about property-based testing. I invite all to come. So in order, what it does is communicate with the exterior. Okay, is the interface part. It communicates with the exterior. So you have essential logic, essential state, communication with the exterior, and accidental state and control. So with those bases there, I don't know how much time I have. Oh, that's good. Almost there. We will have enough time. With those bases there, it starts what the paper calls FRP. Now, who here has ever heard about FRP?
Can you just unplug the screen while you don't use it?
Oh, okay. I'll let you do this. FRP. Who here has ever heard of FRP? So what is FRP? Yeah, no, that's not what the paper said. That's the trick, right? The paper is older than functional reactive programming. So it uses FRP with another completely other interpretation of the name, which is functional relational programming. Okay? Completely other FRP. Complete other FRP. And this approach is the last third of the paper is about this specific approach. So at first the paper shows you how to identify complexity, and then shows a generic approach to fighting it, those separations there, and you could do those in several different ways, right? And then you kind of say, well, in the essential complexity, in the essential part of my code, I could probably go all the way and be very functional, right? And then it goes, in the state part, if I only want to describe state, do I need to be Turing complete? Who here knows what is Turing completeness? Okay, let's go there. Let's go there. Turing completeness is the capability of a language of being a recursively enumerable language. Well, that doesn't help anyone. To being a programming language, okay? A language that is Turing complete, it's a programming language, okay? That doesn't help you yet, but it will soon. It's very easy to create a language that is accidentally Turing complete. It's harder to create a language that you make sure is less powerful than a programming language, okay? And we'll understand together why we should, okay? Well, let's do that before. Let's understand why we should. You cannot reason complexity is the whole heart of this talk is about complexity, and that complexity cannot be automatically optimized away. You cannot create programs that reduce your complexity for you. right? That would be way too easy. You cannot. That's impossible. Okay? As soon as you have a Turing complete language, what you have is a whole bag of possible problems to handle that as programmers you do every day. And if you can get away with solving a problem by not using a programming language, you get in your situation where you don't have all those problems, all that complexity problems. Okay? So if you can use a language that is less powerful, remember in the beginning when I said power is a source of complexity? If you have a language that is less powerful than a programming language, then it can describe less things. Okay, it can describe less things, so you cannot write all the programs you could in that language. But if you all the programs that are relevant to your problem could be written in a language, it means that all the programs that are not relevant to your problem and are impossible to write in that language are not there, and they are all bugs, and they're impossible to be written in that language. That seems a little bit convoluted, right? I should be writing things, but I can't. Writing things, but I can't. So I'll try to do this in another way. NAT, Network Address Transfer Protocol, right? The protocol that translates addresses from IPv4, from IP addresses from outside networks to the inside networks, okay? NAT, as a protocol, is Turing complete. It shouldn't, it really shouldn't, but it is. We have proofs of this now. It is Turing complete. So you could write every program ever in history of mankind using only NAT. That would suck. That would be awful, right? But you can. And the fact that you can, makes it possible to write commands in NAT that are infinite loops. Because if you can write every possible program ever, you could write an infinite loop, right? So if you can write an infinite loop, you can send to your network card something to parse that will make the network card loop forever. Okay? This is a bug. This should not be possible. You should not have to be verifying, am I reading an infinite loop? Because there is no reason why this should be possible at all. Okay? It's like saying, I have an antivirus in my voting machine. Why? Why can your voting machine has virus problems? Yeah, right? You have a problem there, okay? That's the issue. When your language is powerful enough, you have the whole bag of problems of trying to solve the bugs of that language, okay? And by creating a language that is less powerful and still can solve your problem, you're just getting away from all these other possible problems that a language cannot express anymore. Okay? So you can create languages that are less powerful than Turing. It's just very difficult. That is hard. That's why we have NAT as a programming language. It's not because someone thought it would be neat to do it. Nobody found that is neat. Everybody found that's horrible. I mean, I loved it, but that's personal. It made me laugh. But on a professional level, I don't think it's good.
Regarding the easiness of accidentally implementing a Turing complete language,
Yeah.
there was a video going around about the guy who actually implemented a Turing machine in Excel.
Well, yes, of course.
A complete Turing
Machine
machine.
in Excel. It's those kind of people are doing that on purpose. It's very easy to do that accidentally. For example, not and NAND, N-A-N-D, the logical port, not AND, is Turing complete. And hence you can start seeing the difficulty of creating a language if you language is not to be Turing complete. It should not be capable of doing not and. It's very difficult to not do not and it should be useful, right? It's possible. It's just very difficult. Okay? That's the point. It's a hard work to create a not Turing complete language. And a problem of being Turing complete is the halting problem. The halting problem goes at you cannot create a program that takes another program as input and is capable of saying this other program stops someday. This is impossible. You can prove that is impossible. I will not do the proof right now because that will be boring. But for those that want to go deeper on this, you start the proof by passing that program to itself. You just assume that it exists and you pass it to itself. And I'll let you finish the proof. But thing is, it's impossible to know if a program will ever stop without executing that program. But if it never stops, then you have a problem. Okay? As soon as you have a Turing complete language that is used for something, you have at least that problem. So, thing is, when you want to use state, now in our drawing, in the drawing before, we have the separation of control, essential logic, and state, and other, which is just communication with the stereo. When you want to represent state, there is no reason ever, that part of the program that's separated for everything else, there is no reason ever that you need to do a Turing complete language just to describe state. As you shouldn't have to use one just to describe your configuration, just to do your building of your application should not need a Turing complete language, a whole programming language just for that. And just for describing state, you should not need one. Right? And that's the whole approach the paper has to tracking complexity at the heart of software. It separates those lines, and then it tries on each one should have a different approach on how to do it, and those go forward to being 4 different languages that he uses. Okay? And the language that he uses for describing state doesn't need to be Turing complete. It doesn't need to be a programming language at all. So you can create a weaker language that is just there to represent state. So how do you do it? That's where you get to relational algebra. And that's why you call it functional relational programming. Now, when I talk about, don't think about elephants. When I talk about relational algebra, what I talk about is not SQL. I know it's very hard, if you know anything about relational algebra, it's very hard not to think about SQL. Don't think about SQL. SQL is a very bad implementation of this, okay? When I talk about relational algebra, before everything, I'll talk about an algebra. I really saddened that I don't have a screen anymore or nothing to draw anymore because I kind of need one now. But so this talk will quickly become very hard to follow, but I'll try. So in a relational algebra, we have an algebra. So what is an algebra? Okay. That's getting very mathematical. Let's just give ourselves a set of operations that have some properties like associativeness, commutativeness, etc., etc., etc. So you can put the operands in any order, you can put the parentheses in any way, etc., etc., etc. And those operations take the same inputs and they have the same outputs. A relational algebra is an algebra is this, that does that with relations. So everything is relations. So if I want to create an object that is just a student, okay? And another object that is a class, another object that is a school, another object that is a professor. In object orientation programming, each one of those will be an object that encapsulates a state and has some attributes, okay? Here, in relational algebra, each one of those is a relation. I know it's hard. When you do SQL, no, don't think about SQL. When you do SQL, you have entities and relations. Here, you only have relations. So you have not an entity, which is not a table. Don't think about tables. It's something where you put lines, and you have, for each line, you have which entry you have. For a student, you have his name, etc., etc. You have his name, his student ID, etc., etc., etc. For a school, okay. Each one of those relations are what I call base relations. And you have operations that you can use to join those together. Like, you can do a selection filter. You can do a selection. Don't think about SQL. You can do a selection. You can do a join. You can do a... oh, yes, thank you very much. Sorry? Oh, okay. So we can give ourselves things like selects, wheres, grouping bys, etc., etc., and those are not SQL. And those can generate other relations. I take a relation in and give a relation out. So I can generate a whole hierarchy of relations that represent state. Now, I just described one way. It's just the author's way of creating language that can represent all the state of an application. Without being Turing complete. You cannot do whole programs with it. It's actually provable. You cannot write behavior with that, just data with that. You can with SQL. That's why I insist and don't think about SQL, because SQL is actually accidentally Turing complete with some stations. So let's not go there, okay? And SQL, you used to talk with databases. Here, you're talking about your memory state. Here's what the authors want you to do, to describe what you do in memory, okay? And once you do that, what's interesting about this is you only have base relations and derived relations. You can derive one relation from this and another, and another, and another. Just like SQL, you have base tables, and when you do a select, what you are creating is another virtual table that is a projection of the first one, okay? It's the same thing. You're creating relations and projections of relations. But as soon as you do this, then each one of the functions you have created for your essential complexity part, you can create a relation just for it. You can cut out and only have the data it needed. Who here has have objects that has a huge state that goes from parts of the application. In each part that uses it, don't use everything. Right? We all have that. Well, most of you have that. And the whole point is here of not doing that without duplicating the state everywhere. So it starts very strange, but it becomes very elegant. You end up doing very precise definition of states just for one use, but they are projections of a base 1. Thank you so much. Okay. Thank you so much. So, in FRP, functional relational programming, state is just relations all the way down. And those relations described in a non-Turing complete way. And that's the point. Once you do that, and nobody has, that's the point where it's said, right? It tries to give an approach to this, but he did, for the paper, he did an implementation themselves. They did an implementation. But FRP in this sense has not taken off. The goal of the paper was to change the way we do language themselves, to separate those languages in very specific language and not have a whole set of a very big, powerful language we use for everything, but have languages that go together and compose themselves to do specific things and tackle specific complexities. Okay, we are not there. And I don't know if we'll ever be exactly there. But the paper has influenced a lot of languages. A lot of what has happened to Haskell since 2006, which is the date of the paper, was influenced by the paper. And that's easy because one of the paper's authors is one of the people working in Haskell itself. But other languages were very influenced by it too. And F# does lots of things influenced by this. So, yes, I can. Oh, I shouldn't. I should zoom with this, right? Not with my... But even if it has influenced in lots of ways, the specifics of the relational part, aside from a few toy projects, have not been really implemented in real languages. Okay? We have some ways of doing it, and you could try to play with it, but nothing really serious. But the concept behind separating states still remains interesting, and it still has a value. And you should probably, if you try to do it, you probably gain something from it. Even if that separation will not be in a very specific language. Which brings us to the title of the paper itself, Out of the Tar Pit. This is a phrase from Alan Perlin. Beware of the Turing tar pit. Beware of the Turing tar pit, where everything is possible, but nothing of interest is easy. So, it's very easy to see the Turing tar pit when I give you an extreme example, right? When I told net is Turing complete. Well, everything is possible in net, but nothing useful is easy. If you really try to write a program in net, it will be very hard. Okay? A language like brainfuck is Turing complete, but writing programs in brainfuck is made to be hard. It's a puzzle in itself how you do it, right? It's very easy to write useless things, but very hard to write a real useful thing. What the paper authors want you to believe, and it's probably true, even if it's a very hard lesson, is that every one of our current languages is inside the Turing tar pit. Our current tools are very poor. We have language that make very difficult, more difficult, more complex to make things that make sense, and very easy to make things that don't make sense at all. Not as extreme as brainfuck, but that's a very low bar. What it wants to push you to believe is that our current level is still a mess, and we should try to strive for a higher level of constraints, and that higher level of constraints should push you to make it easier to write meaningful things and harder to write not meaningful things. Today, most of language makes, at best, if you are really, really optimist, make both as easy. Okay? So, when it says in the title, out of the tar pit, what it says is, I want you to give a way of getting out of the situation. And that way is by tackling complexity. And one way of tackling complexity is by separating into smaller, those specific chunks which have different behaviors and different reasons why you want to combat those complexities. And the second further way is for having different language for all those 4 chunks. And a further way in the minds of the authors is to make the paradigms different and make the essential part, the domain part, functional. The control part can be anything. And the state part should be a non-Turing complete language. Should be something weaker. No. No, don't go there. Now, thing is, the control part could be anything, but in the paper itself, and that's just an anecdote, that's just not very important parenthesis, but the paper itself, he said, well, if you can do anything, you could probably put another separation identical inside it. It's fractal. Inside the control part, you can split 4 ways again, and inside it can split 4 ways again. And he actually does it by writing, he writes an implementation of the separation that itself in the control uses the separation, uses itself. So you can do it fractally. And you can have applications that have those design, have the communication parts communicate with others that are doing the same way. You don't have to do the whole SI separated in 4, just each application separated in 4 like this. That's the approach the paper has. And, well, I don't think it's very useful, but you could enter in the very detailed, the paper enters a very detailed description of what it wants inside is the part was never done in real life, the relational algebra part. But I really don't know if this is very useful to discuss right now. I'm not very and that's about this. That's about what I wanted to discuss today with you. I don't know. I mean, we have some technical difficulties there, but that's the core of the message. The essential parts are identifying complexity, separating over complexity, separating paradigms over that complexity, and the functional relational programming itself. Okay? We could do some more details. I don't know if you want it. That's my main point here. We could do some more details. What I could offer you right now is why is doing functional reduction of the complexity in the essential domain part. I never entered into this, so we could discuss that if you want. Or why we haven't implemented the relational model in real life yet, or something like that. Those are the kind of tidbits we could enter. But it depends on you. What do you people want? Nothing? Huh? You want PHP? That's not a problem. You can. And that's the thing. The paper wants you to do different languages, but you can do this separation and have different approaches in the same language today. You can be doing mutable objects in PHP. That's possible, right? And you can probably you can do hexagonal architecture with PHP, and you can separate your domain logic in PHP, and you can do a more functional approach in the essential part of the complexity and less functional approach in the control part of the complexity. It gets nearer of what some people call today, one way of going towards there that some people call today is the functional domain and imperative shell, right? It's the having something that is not functional that calls code that is functional. That is an approach that is not as extreme as out of the tar pit, but it's possible to do today. So yeah, you can do this with PHP. And there are some benefits.
Does it also resonate with domain-specific languages?
I mean, you could. You could go as far as creating a domain-specific language for the essential complexity part, right? That's not impossible. I don't know how much of a good idea that is, because there is a whole difficulty around creating domain-specific languages themselves, especially external domain-specific language. But that's probably something to investigate.
Just curious about the internal design, and also something that creating state notation, like record that actually is not Turing complete. I mean, the whole language is Turing complete, but that part of only reference the state is not.
I mean, I haven't tried. That's something I'm curious about. I haven't tried. I haven't tried DSLs on those separations, but that is a rich point that deserves some experimentation. Yes, I cannot help you there right now, but we can try to code this together in the in the next few days if you want. Yes.
So the answer is not 42, but Erlang?
No, no. I tried to not describe Erlang in this. So that is a very sadly pertinent thing to say. I was hoping not to have Erlang people in the audience. So thing is, Erlang did have several of those ideas that he had in the paper some decades before the paper. Yes, the paper is actually from 2006. People usually think it's older than that, but it's really, I mean, it's like 11 years old. It's not really old as papers goes. And some of the ideas there were already in Erlang. Yes, yes. And that phrase is very true to several good ideas every time I do a talk, really. It's awful. I hate that those people, they have all those good ideas before me.
Right, but you basically, we don't have to talk about Erlang, but basically it's the mutable language that is functional, right?
Yeah.
But if you want to take those ideas, and I try to preach this to object-oriented people, you can do this in Java, for instance, which is very object-oriented, with static methods that they find only mutable inputs, right?
You can, I mean, with Erlang you have had the part of having the separation of the communication part and having the it becomes quite easy to separate the state from the essential logic part. But you still have the problem, it's not really relational, right? It's functional programming, but it's not functional relational programming. And nothing is. So you still have the state together. We could separate, but you still have the state together, even if it's immutable state together. And and that's fine. I mean,
But it helps that you can transfer a binary to another process.
no, let's not talk about that.
Sorry.
You can, and let's do that, right? Let's discuss this afterwards. Do you people have questions? Do you people learn anything from this? I'm really sorry about the whole problem we have with the projection itself, but the do you people have any questions about this? No.
I think it's quite a lot to digest.
That's a little bit. Yes. Go.
Philosophical comment. First, how does sort of the idea of essential complexity relate to wicked problems?
Sorry.
Wicked problems, problems that have no single formulation, right?
Oh. Oh God.
And the second one is, does the sort of separation between essential and accidental, is that sort of a Platonic idea?
Yeah. That's true.
Yeah.
The whole idea is that in the ideal world you can separate completely. In the real world, it's very difficult. And I hinted at that during the talk and said, because you cannot call from the essential part, you cannot call the control part, but the control part has to have a little bit of essential just to know that it has to call this first and this afterwards, right? So you kind of have some leaking both sides. All abstractions leak. You don't have perfect abstractions. Abstractions leak. It's just that you have a way here that reduces a lot of that leaking, but it's not perfect. Sorry, you had a question.
I was just thinking.
Uh,
Okay, no problem. I was just considering the leaking part there.
you have a very interesting article about of Joey Spolsky about Joey's laws of leaky abstractions, which he delves into this. But his law is all abstractions are leaky. And the example he gives is if I make an interface that tries to encapsulate something else, okay, and you make that interface, and it's an abstraction, okay, you cannot control who implements the interface. This is something that you, by definition, you cannot control, because if you create it, it's that you want people to implement it, right? And I can always create an implementation that calls a service. You wouldn't know. And the service could always be offline. And then I started having, even if I didn't want it in the beginning, I started having some leaking. Like, all abstractions have some limit. That's normal. That's just the way of life. There are limits to every abstraction. Some abstractions are more harder to leak than others. Interfaces are the easy ones. And you have harder ones, right? Because we could talk about monoids and things like this. And it's really harder to leak that. It's not impossible, just harder.
The thing is that abstractions are sort of always embodied, right? So we can pretend that they're not, and that's what Plato does.
Yeah.
Pretending there is an ideal world.
Yeah.
But in reality, all we have is reality.
Yep. That's the idea. That's the idea. Now about wicked problems. Yeah, I don't have a solution for that at all. Few people have, I think. Well, thank you very much for every one of you.
I have one thing to say. Thank you, Romeu, for coming and joining us. Matthias Verais is coming in August to Oslo to teach his 3 days workshop about the advanced domain-driven design. So if you want to join, there is a link on our meetup site. There is a page about it, and it's also put on the wickedness.no website. So it's 3 days course, mostly about solving the problems in pragmatic ways, about the modeling, including something event storming and different modeling heuristics, tackling software as well, and working with greenfield development projects. So if you're interested, it's a paid event, so after 3 full days, really
Thank you.
Yeah, and if you want to go, there is a gig beer event going right now in Oslo Werkstatt.